¿Puede ver la pantalla?
Se está empezando a compartir. Todavía no. Ya, ahí sí.
Yeah, okay. Good evening, my name is Lucía Moya Tamariz, and tonight I'll be presenting my capstone project titled Parametric Study on the Applicability of ASHTO LRFD for Simply Supported Reinforced Concrete Slab Bridges. I did this capstone project under the supervision of Dr. Eva Lansot. So this is the order of the presentation that I will follow, and now I will begin. So the Merriam-Webster Dictionary defines a bridge as a structure carrying a pathway or roadway over a depression or obstacle. There are many types of bridges, and tonight I'll be focusing on slab bridges, and more specifically on simply supported slab bridges. These are characterized by using a slab as the main spanning structural component, by being economically viable for short spans, and by possessing a large shear capacity. There are two main configurations for a slab bridge. The first one is a straight geometry, where the abutment is perpendicular to the free edge. And the second one is a skewed geometry, where the abutment forms an acute angle with the free edge. So the ASHTO, which are American specifications that guide the design of highway bridges, have two main types of analysis with which these type of bridges can be analyzed. The first one are refined methods that basically consist on refined procedures that satisfy equilibrium and compatibility. One example of these would be the linear finite element analysis. And the second big group of analyses are the approximate methods, and these ones consist on a series of simplified procedures that basically divide a slab into a series of interior and exterior strips. So here is when our two research questions arise. The first one, how does the skew influence shear forces and main longitudinal and secondary transverse bending moments? And the second question is, are the ASHTO LRFD simplified procedures able to capture the effects of skew? So in order to answer these two questions, we conducted a parametric study that considered a total of 80 case study bridges. The cross-section that we used for all of them is shown here in figure 2, and the only variation was the number of lanes. Then the varying parameters are here in figure 1, and they were skew angle, width, and length. And finally, in table 1, you can see the range of variation for each of these parameters. So once we modeled all of these bridges, we performed analyses both through the ASHTO LRFD simplified procedures using hand calculations, and also linear finite element analysis using the software package from SIA Engineering. And then we provided reinforcement according to the reinforcement provisions that are set in ASHTO LRFD design specifications. So this is the loading that we applied for the simplified analysis. And something important to mention here is that the live loading was reduced according to the appropriate equivalent strip width. And then moving on to the linear finite element analysis, this is the loading that we applied. On the top, you can see the loading for the straight geometries, and here on the bottom for the skewed geometries. Also, something important to mention here is that this type of software does not consider any sort of interior and exterior strips, but it rather analyzes the slab as a whole. And now I'm going to mention how we got the design moments and shears when using linear finite element analysis, because it is not as evident as for the simplified procedures. So in order to get the bending moments, we used the effective width principle. To explain briefly this principle, I'm going to show you here this figure 3. So for example, we start with a bending moment profile that can be represented by this function f of x. Then we have to take the integral under the entire profile, and we have to find a width that's going to be called the effective width, that multiplied by the peak of f of x is going to yield the same area. Then once we have found this width, we have to average the load combination, and in that way we would get the bending moment that we were looking for. We did this both for the main longitudinal as well as for the transverse bending moments. However, for shear, we used a different approach. If you can see here in figure 5, for shear, we averaged the peak yielded by linear finite element analysis over a width equal to 4d, and d was the distance to the main longitudinal reinforcement. Also, something important to mention here is that the shear was resolved in the direction of the principal shear, which is normally located, in locations close to the abutment. It is perpendicular to the support line. And then once we finished with the analysis from the 80 case study bridges, we moved on to design. And both for bending moments as for shear, we just used the resistance 1 limit state. And also when we were checking the secondary transverse bending moments, it's important to mention that in the AASHTO LRD simplified procedures, we do not have to calculate any magnitude, but actually the code only provides what's called a distribution reinforcement that, between others, is meant to take care of the transverse effect. So once we concluded with that process, I'm going to give a brief overview of the resultant analysis. So first I'll start with bending moments. If you can see here in figure 6, we were able to see that the bending moment decreases significantly as the skew increases. However, when we were using the simplified procedures, if you can see here this dashed line, we could see that the simplified procedures are only able to capture a small reduction. On the other hand, when we were checking and analyzing the secondary transverse bending moments, we could see that as the skew increased, the bending moments also increased significantly when we were using linear finite element analysis. However, the distribution reinforcement, as you can see here in this dashed dotted line, was not able to withstand the required strengths. So these two phenomena are explained by the principal stresses. When we have a straight geometry, such as the one you can see here in the bottom right, the direction of the principal stresses is parallel to the mean longitudinal direction of the bridge. However, when we have skewed geometries, like you can see here in the bottom left, these principal stresses shift away from the longitudinal direction to the secondary transverse direction, and this causes these changes in the bending moments. Then moving on to shear, in order to compare shear for the two analysis methods that we used, we defined a unity check between the shear demand and the shear capacity. As it can be seen in figure 10, when we were obtaining this unity check for the simplified procedures, we were able to see that all of them were below 0.5 and they were not dependent on skew. However, when we were using linear finite element analysis, we could see that as the skew increased, this unity check increased a lot, and also it almost reached 1 for skew angles of 45 degrees. Once again, this phenomenon is explained by the stress concentration. When we have skewed geometries, there is a lot of stress concentration focalized in the obtuse corners, and this causes this unity check to rise. So then, after we concluded with the analysis of the results, we were able to come up with some recommendations for design. So the first one is that using linear finite element analysis software to analyze simply supported RC slab bridges is preferable because the AASHTO LRT simplified procedures are not able to fully capture the effects of skew. Also, it's important to compare the AASHTO LRT simplified procedures with linear finite element analysis software or other type of more refined analysis in order to know that we are on the conservative side. A third recommendation would be to provide minimum shear reinforcement along the critical shear section that is close to the obtuse corner, because in this way, we will increase the shear ductility of the bridge, even if it would not be extremely necessary extremely necessary because we get a unity check that's below 1. And fourth, it would be recommended to increment secondary transverse reinforcement because, as we could see, the distribution reinforcement is only able to fulfill the demands of straight geometries. And finally, I will conclude with the main takeaways from this project. So the first one would be that main longitudinal bending moments decrease as the skew increases, and secondary transverse bending moments increase as the skew increases, and this is a result of the shift of the direction from the principal stresses. Also, simply supported RC slab bridges have a great distribution capacity of the main longitudinal bending moments. And finally, shear forces increase at the obtuse corner as the skew increases, and this is a consequence of the stress concentration that focalizes close to the obtuse corner when we have skewed geometries. Thank you very much.
Muy bien, Lucía, muchas gracias por la presentación. Felicitaciones por el trabajo. ¿Alguna pregunta de parte del público presente?
Para no perder la costumbre, voy a decir algo, simplemente felicitarte, Lucía, muy buena presentación y muy interesantes todos los resultados. No, ninguna pregunta, simplemente una felicitación.
¿Algún otro comentario o alguna pregunta?
Sí, tal vez el modelo, el programa que utilizaste para el Final Element Model, me parece que dijiste CIA, el programa, por favor, el nombre.
Engineering. Se llama CIA Engineering, es un software de acceso libre y es muy usado en Europa.
¿Cuál es el nombre del programa, perdón?
CIA, SCIA Engineering.
¿Es de libre acceso?
Sí.
No había escuchado que es de modelación para elementos finitos o de qué es, o es de
Sí,
qué
o
se
sea,
trata.
puede hacer análisis lineal, también análisis no lineal, y como estudiantes o docentes hay como tener una versión, o sea, una versión gratuita que permite hacer la mayoría de funciones del programa.
Interesante. No había escuchado eso.
Si no hay otras preguntas, quería agradecer a Lucía por todo el trabajo que ha hecho. Ha sido un trabajo bastante complejo, ha hecho bastante cálculos, lo ha manejado de manera muy independiente y como resultado de eso también ella ha escrito un artículo que en este momento está bajo revisión, entonces tenemos los dedos cruzados para recibir pronto los informes de los revisores.
Me alegro mucho. Felicitaciones tanto a Eva como a Lucía. Bien, si no hay ningún otro comentario, damos por concluido la segunda sesión de defensas o presentaciones de los trabajos de graduación de los estudiantes de la carrera de Ingeniería Civil. Gracias a todos por su presencia. Mañana tendríamos la última sesión en el mismo horario. Una vez más, felicitaciones a todos los estudiantes por las presentaciones. Todos los trabajos estaban bastante buenos. Y pues nada, ahí concluiríamos la jornada de hoy. Buenas noches con todos.
Muy buenas noches y que estén celebrando este día.